Hi everyone, welcome to this series on feature engineering for data science and machine learning. In this video, we shall be covering another topic under filter method under the category of feature selection techniques. As you know, the feature selection methods typically focus on understanding individual columns and providing descriptive statistics of the column, thereby removing irrelevant and redundant columns. Essentially, we get reduced set of features for our machine learning model. So the topic is going to be univariate feature selection methods. That previously we have covered variances, covariance, correlation, and important side topic with correlation was your multicollinearity assessment and impact of multicollinearity in your data and on the model. Types of correlation that we use typically in data science, Pearson's and Spearman and Kendall-Tau. We also covered another filter method called information value. I have provided you with the context on univariate feature selection along with the recap on hypothesis testing. In this video, we'll talk about a few of the methods that are popularly used under univariate feature selection, namely TTest, chi-square, and ANOVA, and few more. But we will be covering the first three, which is TTest, ANOVA, and chi-square. Okay, so what is t-test? Is a statistical method to check if there are differences in your data in terms of mean. Let's look at now some examples and a little bit more detail. So the definition of t-test is actually a statistical test which compares the mean of two data columns or the two groups. And the groups can be something like, for let's say a class of 0 and class of 1 and the associated continuous variable, let's say length, and the length for group 0 and length measurements for group 1. And these are two groups, and you would like to check if the mean of these two groups are similar. Why do we need to compare the means of two groups? Essentially, for feature importance, understanding the feature importance and selecting column. One of the major phases of data science is to understand which columns are useful, which ones are not. So if there are significant differences in the mean, then we know that column is useful. Why so? In machine learning, we want the columns to be discriminatory, and we should have distinct means between the groups, and that contributes well towards the model performance. That's one reason, and the model evaluation can be another reason why we want to do the mean comparison. For example, let's say, here we have two different models, or let's say the model is M1, and the metric that we obtained is mean squared error. And here is the model 2. Again, we got the mean squared error. Now, these two models are different in terms of maybe, let's say, parameter or something like that. And then we would like to see if the mean of the measure for M1 and the measure for M2, so the mean of M1 is equal to the mean of M2. If that's so, then you know that these two configurations of the model is really not different. If they are different, then you know one of these model is better than the other. So that would be another use case why we need to compare the mean of two different groups. Let's take another example here. Suppose we want to test whether there is a significant difference in the scores between the two groups of students. Now, these two groups of students, they followed different methods of study. Let's say the group A used traditional method to study. Group B used slightly advanced online method. And they performed, and you have the scores for group A and group B, and you would like to check if the mean of score of group A is similar or same as the mean of score of group B. So that would be another use case of the need to compare the means. Now we have something called hypothesis here. When you have a mean of group A and group B, we say that there are no significant differences. That's called null hypothesis. And the alternate or counter hypothesis is called H1 or H, sometimes is called HA, when the mean of A is not equal to mean of B. That means they are different. So that's called alternate hypothesis. Now, when you conduct a test, you need some sample data. Let's say the scores for group A and scores for group B here. Then we use statistical method, let's say t-test, and on this data, and we get the t-statistic. Now, using the t-statistic and also the degrees of freedom, which is another statistical concept, which is essentially in this case, the length of group A, length of group B, and -2, that gives you a degrees of freedom. With that, these two measures like t-statistic and degrees of freedom, we get the probability value or p-value. If the p-value is lower than the significance level, like typically set to desired level, sometimes 0.05, sometimes if the model is very extremely complex or critical, then we go with slightly lower number, let's say 0.01 or even lower than that. If the p-value is less than the significance level, then the null hypothesis is wrong. That means the mean of A is not same as mean of B. That means we are saying there is significant difference in the average scores of the student. For example, here one sample t-test, and this curve that you see is a distribution of probability. T-statistic is the blue line obtained from the statistical function based on the sample data that you provided. And that red line that you see here is a line for critical value. This critical value is for significance level that we have set, let's say 0.05. Now, if your t-statistic is more than the critical value, that means this is the region here, and this region is called rejection region. And if your t-statistic falls under the rejection region, then you can reject the null hypothesis, which is H naught. And H naught, typically we say the mean of A is equal to mean of B. And then you say that no, this is not true. The mean of A is not same as mean of B, so we reject the null hypothesis. Now, there are various types of t-tests that are used. One is called one-tailed t-test. For example, here you see here there are two tails. Okay, so the rejection region would be on both the sides. For example, here, so this is the critical value. Similarly, you would have critical value corresponding to this mean on this side as well. So this is another rejection region. This is another rejection region. One more. So there's like two rejection regions, and this is called two-tailed test. Now you could have one tail as well. So let's take a look at some examples of one tail. For example, if you're saying the group A is significantly higher, we're not saying different, we're saying the group A scores are significantly higher or lower, either. So when you use higher or lower, that kind of directional intent, that's called one-tailed t-test. And two-tailed is non-directional. It can be either greater or can be lesser. So let's take a look at some examples of one-tailed t-test. So is the average score of group A greater? Does the new drug lead to a decrease in the blood pressure? Decrease, okay. So that's the one tail. Is there a significant difference between the mean response time where A is slower? Okay, so that's directional intent. Now, similarly, two-tailed t-test. where there is no directional intent. So you say, is there a significant difference? Are there differences in the average, customer satisfaction scores? Similarly, are there significant differences? So when you have a very general intent saying that whether the means are really different, right, from each other, then that's called two-tailed t-test. Depending on the problem or the objective, you would use either one-tailed t-test or two-tailed t-test. Now, t-test can also be used for with one sample. So let's take a look at what is one sample then. One sample example, let's say, you have collected the blood pressure readings of some patients, and then you want to compare. Typically, the blood pressure reading is going to be 130, is considered mean, and you want to see whether the mean of the patients here is equal to 130 or not. That's called one sample t-test. Two sample t-test would be like two samples. Let's say patient from some country here, another group of patient from different countries, and you want to see whether the blood pressure readings from these two countries are same or not. So that's called two sample t-test. Now, important criteria that you need to consider is also the type of samples that we use in the t-test. For example, the first one is independent sample t-test, means you are drawing the samples from the independent pool of samples or population. For example, it would be scores of students from two different schools, like, these are different pools altogether. So that's called independent sample t-test. Whereas the paired sample t-test is dependent. That means the same student, group of students, given one option to study, and the same set of students given another option, another, maybe the study material, and then you compare these scores. Similarly, let's say the patient, a group of patients applied one medicine, the same group of patient after some time, applied the same medicine or different medicine, and you would like to compare uh, the measurements basically of the same patient at different time. That would be a paired sample t-test. So most of the data science and AI work that we encounter is going to be mostly independent sample t-test, unless it is a medical domain or some pharma domain or some other specific domain. You might have to think about paired sample t-test. So before I show you the Python implementation of t-test, there are some assumptions. So of t-test, typical t-test, they should follow a Gaussian or a normal distribution. But this typically is not so important. If you have large number of samples, let's say 100, 200, or 500, then this normality requirement is not needed. Data should be randomly sampled, independently sampled from the population. It should not be based on any pattern. Scale of measurements should be continuous. The t-test is only for continuous data. Homogeneity of variance is another requirement. That means the variances of two groups should be more or less the same or equal. And that's where the t-test will actually work. But if these assumptions are violated, then we have different options or different type of t-tests or optional or variants of t-tests that we apply in those situations. Okay, so now I'm going to show you the Python implementation to show some of the variants of t-tests. Okay, so now let's look at some of the variants here. So we're going to talk about a few variants here. So first I'm going to show you one sample t-test, then two sample t-tests, one sample left, and two sample left, just to illustrate the different types of t-tests that we use. Okay, so here is NumPy, and the t-test functions are part of your SciPy package, TTest, one sample TTest. And this T is another library which gives you a t-distribution, which I'm going to show you. And this t-distribution is used for plotting. So this is my NumPy and Pandas, and the main, statistical package is part of your SciPy. First, I'm going to show you the one sample t-test. This is the internal, working of the t-tests, which we are not going to do manually. We'll just use the package, but the package is going to apply this kind of formula within. We just need to pass the data. So we need to set the null hypothesis and the alternate hypothesis. So let's say the null hypothesis is the mean blood pressure is 120. The alternate would be not equal to 20. And we collected some sample here of the female, patient's blood pressure. And let's say the hypothesis is the population mean is actually 120. Now we're going to pass these two, the variables which has the data and the population mean. And this is going to be one sample. Okay, so and this is going to be returning the two things, the t-statistic and a p-value. P-value is very less, 0.002, which is actually much lower than the significance level. And typically by default, the significance level is 0.05. So this p-value is lower than 0.05. And when it is so, we can reject the null hypothesis. That means what is the null hypothesis here? The blood pressure readings are actually equal to 120. Now we are rejecting this. So that means the blood pressure readings that we collected is not equal to 120. It is something else. Okay, so that's the purpose of this assessment. So alpha is 0.05, which is a significant level. Now the degrees of freedom is nothing but the number of samples that you took. And since it is one sample, so just one sample here, -1, that's the degree of freedom. And using the degree of freedom, we get the critical value. So let me show you in terms of plot. I'll explain what we actually achieved by this test. So this is your t distribution, and this is my critical value at alpha equals to 0.05 on both the sides. So here also alpha is equal to 0.05 on the lower side. This is on the higher side. So the blood pressure reading, if the p-value falls in this region, either the p-value or the statistic falls under this region, either here or here, we say the null hypothesis is wrong, can be rejected. So notice here, in this case, the blue line, which is our test statistic based on our data, which is actually more than the critical value. That means this is in the rejection region. So we reject the null hypothesis. Okay, so the critical region is shaded and the vertical line illustrate that particular point. Now, so one more variation of a t-test is two-sample t-test. Again, the two-sample t-test, we just need to make some changes to the arguments, and internally the package is going to do such complex operation, which we don't have to do here. So here also the null hypothesis, since there are two groups here, so we say that the mean of group 1 and the mean of group 2 are both are same. Okay. Alternate would be they are not same. So let's say we have two groups here, and now sample test, and here we are passing both the samples. So this package will know this is actually two sample t-test. And then it returns a p-value, which is again much lower than the 0.05 significance level. So we say that the mean are not equal. So because we are rejecting the null hypothesis. And the null hypothesis is the mean of male is same as mean of female, which is not the case because we are rejecting the null hypothesis based on the experiment. Again, this is a plot, and the plot is clearly showing the same. The green line is your t-statistic, which is on the extreme side, and we reject the null hypothesis. Let's take a look at one more here. One sample left-tailed. So it's like, directional. Now we're saying lower than. So let's take a, same data here. And the mean is this, 110. And since this is left, that means we are saying uh, the um, the female blood pressure is lower than 110, and the null hypothesis is going to be equal to 110 or greater than 110. That's the null hypothesis. Very important to set the null hypothesis correctly. Otherwise, you would conclude, um, opposite way. Now, this is t-test here. Pass both of these, and now you see here another additional parameter which was saying alternative equal to less means lower, left-tailed. And the package is going to use that and return the p-value. P-value is very high compared to 0.05. So we are not going to touch the null hypothesis. That means the null hypothesis actually holds true. That means the female blood pressure is not less than 110. This is equal to 110 or greater than 110. Similarly, one sample right-tailed, same data set here, and hypothesized mean is 110, and here is significance level. You can change it to 0.01 or any other. And now notice here I'm saying alternative is greater. Greater means right-tailed. And what's the value? Very, very small value, much lower than 0.05. So we reject the null hypothesis. And the same plot, just a little bit of a change in the code, but it's just going to do this. It's actually copy paste from the previous code. And you notice here, the one sample right tail t-test here, this is the critical value, and the value that you get here on the extreme end, that means you you can reject the null hypothesis. Two sample t-tests, two sample left-tailed, that means you're saying one sample mean is lower or higher than the other sample mean. So how do you do that? You just take the two series here, alpha and the t-test, pass these two in the exact order, like female first and the male here. So because you're saying female is lower than the male reading. Okay, so it's important to put them in the right order. And less is the direction. That means it is smaller. So you're going to get 0.99. That means you cannot reject the null hypothesis here. All right, so I hope you understood the basic idea of t-test here. I can show some other examples as well, but that will be in a different video. I hope it is clear. Okay, so so I showed you how to implement the t-test in Python using SciPy. There are some assumptions to make sure that those assumptions are met before you apply the t-test. If the assumptions are violated, then you cannot apply the t-test that we just discussed. There are different variations and alternatives to t-tests. The next feature selection, univariate feature selection method that we will talk about is ANOVA, but that would be in a different video. Thank you for your time, and we'll see you in the next session.